It has started recording. My pen seems to be working. Okay. So, guidelines for curve sketching. We're going to make basically, or you have in front of you, a one-page summary of everything we've done so far. We're going to take this summary and put it into action today. When given a function, the first thing you want to do is identify the domain and range of your function. And are there any non-permissible values? Do you have a hole in the graph? Do you have an asymptote in the graph? Or do you have any restrictions in your domain? Before we even start curve sketching, we need to know what is the greater picture? What is the bigger picture that we're looking at? Where are we expecting this to go? Okay, then we are looking for intercepts. Means we are going to find where is the original function 0 and what makes the original function 0. For what values of x make it 0. So we're essentially looking for x and y intercepts if they are easy to solve. Sometimes they are a big pain in the butt and we will use technology. Most of the time you will get nicer questions. Okay, then we're going to look for symmetry. This one is kind of less useful because not all of the graphs that we're going to be looking at are going to be symmetric. However, if they are symmetric, it does our work in half. Because if we know that there's a maximum on one side and it's symmetric about the y-axis, we know that there will be another maximum on the other side of the y-axis, right? And the test for this is if you put negative x into the original function, do you get the same number as if you put a positive x in? If you do, then we have an even function about the y-axis. So if you think of a sine or a cosine graph that starts at 1 and goes down and to the right, down and to the left, this is an even function because it's like a mirror image about the y-axis. Okay, now if you put a negative x and what you get is the negative of, so a negative y, the opposite value of if you had put a positive number in, we call this an odd function. And the way that we can think of it is like a sine. Sine starts at 0, goes up, but then if I go backwards, it goes down. So it's like a mirror image, but it's symmetric about the origin rather than about the y-axis. Okay, so this is an odd function. Okay, so symmetry will help us sometimes, but not always, but it is something we are going to check for. And the last thing we want to do, again, this kind of relates to the domain, is we want to know, are there any asymptotes? And the way that we are going to test for them, for vertical asymptotes, it'll be a little bit easier. You are looking for non-permissible values in the domain. What makes the denominator 0 if a denominator exists? Okay. And then for the vertical asymptote, we're going to use limits. You are going to take the limit of your function as x goes to infinity and negative infinity and see if it approaches a number as we did in section 1. Okay, you'll notice that these 4 words, there's an acronym we use, SAID, said. These are things we are going to inspect before we even do derivatives. We are looking for symmetry, asymptotes, intercepts, and domain. Okay, and all of these 4, we are inspecting them based on the original function f of x. Once we have these pieces of information, then we move on and we look at f prime. So this is where we inspect f prime of x. Okay, so we are going to look at intervals of increasing and decreasing. Means we're going to find our critical points and we're going to look at, we're going to use the intercepts from the f function and we're going to test those intercepts on the left and right side. Right, so intercepts from the f function, and we're going to see plus minus, which means we are increasing, decreasing, increasing, decreasing, or something to that effect. Okay, and we are going to look for local maximums and minimum values, and these are the critical points of where f prime of x is 0. We're going to look for where is the derivative, the first derivative 0. And then lastly, the last two things we're checking for is f double prime of x. We are going to take the critical points we found here, and we're going to put them into f double prime. And we are going to determine, do we have max or mins or inflection? Okay, if we have a maximum, then f double prime will be negative, meaning that we have a max going down. If we have a minimum value, that means we've reached the bottom and we are now moving up. And if we have an inflection, means the derivative on both sides is in the same direction, but we have a slight like S curve through. Okay, so this is our summary page. Let's put it into practice. Let's take a look at the next two examples. Sketch this curve. We're starting off easy. Notice that I can rewrite this as x cubed 3x squared minus 5. The reason I did that is to find the x-intercepts hopefully easier. Okay, so I have domain is x is all reals because this is a polynomial function. I also have a range of y is all reals, again, because I have a polynomial function. It is an odd function, not necessarily symmetric, but it is an odd function, meaning that I have one arm going down, one arm going up, right? We can test to see if it's truly an odd function, a symmetric odd function, by looking at symmetric. Let's say we put in f of negative x. 3 negative x to the 5th minus 5 negative x to the 3rd. This will give me negative 3x to the 5th plus 5x to the 3rd, which is the same thing as the negative of the original function. So we do have symmetry, and it is odd. So it's going to have some kind of symmetry where whatever the right side does, the left side will do in the negative. So it has something like this. Because this is a polynomial function, right? So I'm going through the SAID, S-A-I-D. Asymptotes? None. Intercepts? Well, let's take a look. If y is 0, what x value does that give me? X would have to either be 0 or plus or minus root 5 over 3. Okay. So what is the domain? Oh, I already did domain. Okay, perfect. We did all the first bits, all the information we need from the first one. Hold on. 0, 0. Root 5 over 3, 0. Negative root 5 over 3, 0. What about y-intercept? 0, 0. Okay, so I have my intercepts all done. I just had to make sure there. Okay, let's take a look at f prime. f prime of x is going to be 15x to the 4, right? Because the first one is a 5, okay? And then I'm going to have minus 15x squared, which means I can factor this out. This is x squared minus 1. Okay, and if I want this to be 0, yes? Could, I don't need to though. Because I'm just looking for zeros, right? Yeah. Okay, this tells me that I have critical points, CPs, where x equals 0 and plus or minus 1. Okay, so critical points at x equals plus or minus 1. Let's take a look here. 0, plus 1, minus 1. I know that I have a peak and valley or an inflection at these 3 points. So what I want to do is figure out what is happening on the left and right side of these points. So what I'm going to do is I'm going to check f prime at -2, f prime at 0.5, negative, f prime at positive 0.5, and f prime at 2. And I'm not interested in the number I get. I'm only interested in plus or minus, increasing or decreasing. That will tell me the direction of my lines, right? Okay, so grab a calculator. Oh, I have one in my hand here. There we go. So 15 times, again, make sure you're using brackets here, -2 to the power 4 minus 15 bracket -2 to the power 2. And I get a positive value on this side. And if I do this all again, I'm going to go insert point. Insert point. Okay, between -1 and 0, I'm getting a negative value. If I do this all again for the positive side, I'm going to get a negative value here. And I get a positive value here. Okay, so what this is telling me is the derivative. I am increasing on the right side of -1, decreasing on the right side, or the right side of 0, decreasing on the right side of 1, and then increasing on the left side of 1. So you can kind of gain a picture here as to what we're looking at. Likely this is a max, likely this is a min, and likely this is an inflection point, right? What I'm going to do is I'm going to put this into f, the original function. Let's figure out what these coordinates are. Zero, 0, we already know. If I put -1 into my original function, what am I going to get? -3 plus 5. That gives me a 2 here, which means I'm likely going to get a -2 here because it's symmetric, but opposite sign, right? So this is -1, 2, and this is +1, -2. Okay, so I now can say this is my max, this is my min, and this is my inflection. most likely. Okay, next thing we want to do is we're going to take our critical points and we're going to throw them into F double prime to see where is the change of direction as we come down through the max and mins. Okay. What color did I do double prime on the last page? I think it was pink. Okay, F double prime is going to equal. I start here and I do this second derivative. 4 times 15 is 60. X cubed minus 30x. Or actually, I don't need to simplify it because I'm just going to test the critical points. Okay, so now what I'm going to do is I'm going to test F double prime at its critical points, 0, F double prime at 1, F double prime at -1. And again, here I'm just looking at positive or negative, concave up, concave down, and what do I get here? So if I put 0, I get 0 again. If I put +1, I get a positive number. If I put -1, I get a negative number. So this tells me that I have a min and a max as confirmed before. And where this is 0, we are going to have a change in direction. F double prime is 0 when x is 0. And where else? Let's see, if I pull this out, I get 30x. No, 2x. 2x squared minus 1. So then this is going to be giving me x is plus or minus 1/2. So I'm going to have a change of direction at plus minus 1/2. Okay, what that means is, oh, square root, oh, thank you, yes, square root 2. I want you to think of like a sine cosine graph. When you go up to the top, down, down, like this, when we do sine waves, right? On this interval, go away. It is decreasing. But can you see how there's a bit of a change of direction? This is concave down, this is concave up. So although it is increasing from end to end, there is a bit of difference in concavity. So that's what F double prime is telling you. Where is that switch in direction? Where is that inflection point? Okay, we have all the pieces of information we need. So let's take a look. At -1, we have a max of 2. At 0, 0, we have an inflection. At 1, -2, we have a minimum. And before and after that, we are increasing, decreasing, and whatever. But notice also that we have an inflection in positive and -1. So actually what I'm going to do to make this a little bit easier to see, let's spread this out. Let's say 1 is over here. 1, 2, 3, 4, -1 is over here. So this is -1/2, or root, I guess it's technically before that, positive 1 over root 2. -1 over root 2, something like this. Okay, so I have 2 inflection points. Before -1, I have a graph that is increasing to that point, and a max at -1, 2. -1, -2 here, okay? So I have a graph that is concave like this. And then it continues concave until this point. or until this area, I should say. And then it kind of curves down like this. And then I have again like this till we go down. Oh, this is not a very good picture, guys. Sorry. Yeah.
You know how like your graph is curving down after -1?
Yes.
But we didn't get that the x-intercept. Isn't it just going up instead of coming down and the x-axis?
Say that again. Did you sort it out?
I figured it out.
So we have x-intercepts here, here, and here. We have 3 x-intercepts. We have 3 inflection points, and we have a max and a min, right? Let's see, is root 5 over 3, oopsie, root 5 over 3, what is that? 1.29, and then 1 divided by root 2 is 0.7. Okay, so we have something here and something here. This is root 5 over 3, negative root 5 over 3.
You know how like your graph is going down to the -1? Like it's going down and hitting the x-axis.
Mm-hmm.
But we didn't get an x-intercept that would make sense over there. So the graph will go down with this. We don't have an x-intercept there.
Wouldn't go down if I didn't have an x-intercept where? Sorry, say that again.
I think I'm waiting to write that. That should not hit that.
Oh, I see what you're saying. Okay, yeah. Okay, yes. I hear you now. Apologies. Okay. Let's say 1 is here, doesn't really matter. Okay, let's do this again. 1 and -1. We know we have an x-intercept at 0. Our other x-intercepts are root 5 over 3. Root 5 over 3 is 1.29. So that means our x-intercepts are actually just after 1. My apologies. This is root 5 over 3. This is positive root 5 over 3. Here are our intercepts. Okay, our maximums occur at -1, 2. Okay, let's just go up by 2's here. And 1, -2. So these are our max and our min. Okay, and then somewhere in between, we have 1 over root 2, 1 over root 2. These are our inflection points. Okay, so what this is saying is this. I have a curve that's going like this, and then it like this, and then as soon as it crosses this boundary here, it now goes like this. Is that better? Yes. Okay, and then our inflection point is also at 0, so now it's going like this. And somewhere over here, it stops going like this, and now it goes like bowl up. Yeah? Okay, and then it continues to bowl up and goes that way. So our inflection points are here, here, and here. Our max and mins are here and here. And then we have intervals of increasing and decreasing in between. Sorry, in my brain, for some reason, I had 5 over 3 was less than 1. That's why my picture was starting to be weird. I apologize. Thank you for catching that. So our x-intercepts are the far corners and the middle. And we have points of inflection in between where it kind of switches direction. We have 15 minutes. You may choose which example do we want to do. Do we want to do number 2 or number 3? You picked. We'll just do one. Number 2 or number 3?
Which one's harder?
3 is tricky, but visually I think 2 is harder because you have asymptotes that you don't normally have or that we haven't really done too much of. Do we want to do number 2?
Why don't we just do it like one? I don't think you're gonna rush to it and you're not gonna.
Well, I won't rush. I will do only as much as we can get to. So which one do you want me to get started? Okay. 2 is a rational function. So right away, we know we're going to have something in the denominator that we cannot be, right? So I'm either going to have a whole or I'm going to have an asymptote. You tell me which it is. Asymptote. Asymptote where? Right. So x is plus or minus 1 is an asymptote right away. We know we're not going to cross that boundary. Okay. Any other things we should worry about? I don't think so. So let's take a look at the intercepts. If y is 0, what values of x will make that happen? Okay, so 0, 0 is an intercept. If I put x is 0, well, I guess that takes care of that too. Okay? Only one intercept. It is both the x-intercept and the y-intercept. So that was a 2 for 1. Easy. Okay. Moving on. Let's talk about symmetry. What happens if I put negative x instead of positive x? Do I get a different answer or a same answer? I get the same answer back. So this is symmetric and it is even because they're squareds, and you can put positive, negative is going to end up positive. Okay, so we're looking for something that is a mirror reflection over the y-axis. Okay, we know where the function is 0. Let's look at the derivative. Y prime. The 4x times x squared minus 1 minus 2x times 2x squared all over x squared minus 1. Did I do that correctly? Agree? Oh, yes, denominator all squared. Thank you. Yep. So I end up with 4x to the 3 minus 4x minus 4x to the 3 all over x squared minus 1 all squared. And you can easily see that cancels. So this is all I'm interested in. That's y prime. Okay, let us use y prime to identify what is happening on the graph before and after 0. I'm also going to check before and after positive and negative 1 because I know that I have asymptotes here, right? So I know that something is happening on the other side of them as well. So what you want is to test y prime of -2, y prime of 0.5, y prime of 0.5, sorry, the first one should have been -0.5, and then y prime of +2. And you're looking for, is it positive or is it negative? What did you get for the first one? Should be positive, yeah? And then the second one? Positive again. And then the next one should be negative. And should be negative. Okay, so we have an intercept at 0, asymptotes at 1 and -1, and now we know the intervals. On the left side, it's increasing. On the right side, it's decreasing. So let's move on to double prime. Y double prime. Derivative of the top times the bottom unchanged minus plus the top times the derivative 2x all over x squared minus 1 to the power 4 now. This one's a little bit uglier. Is it worth me expanding it? I don't know. Let's just try not for a second. X squared minus 1 all squared plus 4 times 2 times 2 is 16x squared. X squared minus 1 all over x squared minus 1 to the 4. I can reduce by 1. Not the prettiest thing, but as simple as I think this is going to get. So this is going to be negative. Oh, and then I can expand the brackets. Negative 4x squared plus 16x squared is what? 12x squared, right? Negative 4x plus 16 is 12. X squared plus 4 all over x squared minus 1 to the power 3. So here is f double prime. Okay, at the critical point 0, y double prime of 0, that was our critical point from y prime, is the value going to be positive or negative? It's not going to be 0. It's negative. So that tells me that I'm starting at the top of a hill going down. So this is going to be a maximum. Can you put it on my desk? Okay, just give me one moment. Okay, so then let's check what is happening at the other critical points like the asymptotes. What is happening at y double prime of 1 and y double prime of -1? Yes, so try slightly to the left. So try 1.5, negative 1.5, or -2. We can't be at those points because they are asymptotes. So go slightly to the left and slightly to the right of the asymptote. We know that 0 is going to give us a maximum, right? It's going to look like this. But what's happening on the other sides? When y double prime is positive, you should get a positive number, meaning it's concave up. And you should get a positive number here, meaning it's concave up as well. Okay, so it's not telling you there's a max or min, it's just telling you that it's going to swoop in that direction. Okay, so let's take a look. On our chart, I'm going to use every 2 to equal 1. So this is 1, 2, 3, -1, -2, -3. I know that I have an asymptote at -1, +1. I know that I only have an intercept at 0, 0, and that 0, 0 represents a maximum. Therefore, it's going down like this in that interval. Okay, now, what's happening on the other two sides? If x is a large negative number, take a look at this. Can y be negative? If I put negative numbers into x, can y be negative? Can I get a negative y value?
No.
No. So that means if it also is positive, then it's also going to be positive. So that means I have only positive values. So somewhere on the left side is a graph that looks like this. And somewhere on the right side is a graph that looks like this. It has to be a positive value because of the function. And it has to be concave up because of the double derivative. The only point we know is 0, 0, and the asymptotes. Everything else is a guess. Okay, that is all for today.